Hi, it's Renata here. If it's your first time here, welcome to my channel, The Quanti Girl, where we are going to talk about some topics in applied mathematics, in pure mathematics, in quantitative finance, and in Python program, because I'm a PhD in mathematics and a financial quantitative analyst, and I'm here to share with you some of my experience. Today we are going to use Python to price a European spread call option on the difference between two stock prices. The stock prices that we are going to consider here are two indexes prices, and the indexes that we are going to use are S&P 500 and Nasdaq index. For our purpose of pricing our European spread call option, we are going to use the Monte Carlo simulations, and we are going to use the Heston model to model the stochastic volatility of the stochastic differential equations for the index's price. So under risk neutral measure, the underlying stock prices, the underlying stochastic differential equations for the stock prices are given by the two equations that you can see in the screen, and the variance processes are also given by two stochastic differential equations that you can also see in the screen. And we have a correlation matrix between the Wiener process that we are going to denote by ρ, and you can see ρ in the screen. We need to introduce some notation here, so we are going to denote by ST the index's prices, by VT the variance, by C the European call option price, K the strike price, W a standard Brownian motion, R an interest rate, delta a dividend payment in discrete time, K a mean reversion rate, theta a long run variance, V0 the variance in the initial time period, sigma the volatility of the variance, ρ a correlation parameter, T today date, and big T the maturity date of the option. So now we have everything that we need to code our simulation of the price of our European spread call option. So just keep watching the video and code with me. So let's start coding our simulation in Python. The first thing that you need to do is to import the libraries that we are going to use. So let's do it. We are going to use the SciPy. Actually, we are going to use the Koleski from SciPy line alg. We are going to use NumPy. We are going to use time. And we are going to use the matplotlib to plot the results in the final of our simulation. Now we are going to specify some parameters using as reference today, the day that I recorded this video. So let's specify Nasdaq. You also need to specify S&P 500. You need to specify Nasdaq and the S&P 500 dividends. We need to specify K. K is the difference in points from the two index that we are going to use. We need to specify a time period. Let's consider just 1 year. And we need to specify the interest rate. It is the 10 years US Treasury bond yield. Now we need to specify the parameters for the Heston model. We are not going to explore today how we can get these values, but we can talk about it in some video in the future. So we need to specify the thetas. The kappas. The kappas, remember, are the mean regression parameter. And the volatilities that we are going to denote by sigma here. So let's move on, and now I need to specify the variance in the first period. Now we need to write the correlation matrix. Let's denote it by rho. And we are going to use the NumPy to write it. Okay, let's write the second row. Now the third row of the matrix. And finally the last row. Okay, let's run. Okay, there is not a queue here. Yeah, I just forgot to put brackets here. Okay, let's move on and specify the Monte Carlo parameters. So the first thing that we are going to specify is the number of steps of our Monte Carlo simulations. So let's denote it by M, and let's say that we are going to consider 200 time steps. Now I need to specify a number of simulations. Let's call it by M, and let's consider 2000 simulations. Now we need to specify constants. The only constant here that we need is the equal spaced time steps. It's just t, the time period, divided by the number of time steps that we denoted by n. Now let's write Haston model adjustment for the time steps. So kappa 1 adjusted by time steps dt is kappa 1 times the time step. The same for kappa 2. And the same for the volatilities. Now we need to write the classic decomposition. So we are going to call the classic function. Parameters are the correlation matrix rho, and we are going to consider the lower decomposition. Now we need now to generate correlated Wiener variables. So let's denote it by z, and let's call the random point normal function from NumPy. The parameters are 0 mean, variance 1, and the shape of the matrix. So now let's write the Wiener variables. We are using matrix here. Now let's write an array to store prices and an array to store variance. We are going to use the full function from NumPy. And the shape is the number of time steps n plus 1, and the number of simulations that we denoted by m. And we need to fill values. Fill values as the log of Nasdaq. Now we just do the same thing for S&P 500. And now we fill values with the variance. The variable we need are these two, the variances in the initial period. Same thing for the variance of the S&P 500. Let's move on, and now we need to write how to compute the expectations and the standard errors. So we are going to use a loop here, and the range that we need is the number of time steps. So we need to simulate variance process. Remember these stochastic differential equations that I'm writing here now are the stochastic differential equations for the variance process that we have saw in the first part of this video. Now we need to write the same thing for the variance of the second index, that is S&P 500. Forgot a parenthesis here. Okay. Now we need to write the simulation for log asset price. So let's annotate it by new. First, let's write for Nasdaq. And we have the same thing for S&P 500. So now we need to take the log. And you write the same thing for S&P 500. And now we just take the exponential from these two variables that we defined here. Finally, let's write how to compute the expectations and the standard errors. Okay, now let's write the volatility and the standard errors. We need to divide by the number of simulations minus 1. And finally the standard error. So let's check that the code is working. Yeah, so we have that the value of our call option is this value with the standard error of minus or less 30.42. So now let's plot our simulations. So I need to specify the timing. We need to create a figure. And we are going to use matplotlib for doing it. actually we need is 4 plots in one plot, so we are going to use the function subplot, specifying 2 rows and 2 columns and a size for our plot. Okay, let's move on and start to write the code that actually plot what we want. Let's specify a title for each plot. So let's go to our second plot. So I need to modify the asset here. Remember, ST2 is representing S&P 500. So finally, let's plot the volatilities. Let's define a title. And finally, the same thing for S&P 500, the volatility of S&P 500. Finally, let's just define a title for the whole plot. Finally, you need to call the show function from matplotlib. Okay, let's run. Okay, it's not figure size, it's figure size here. And I think it's okay now. No. Okay, we need an X here, of course. Okay, here is title. The same error here. And finally, I think it's okay now. Yeah. So we can see here the results of our simulations. So we can see here the stochastic volatility for our spread option. That's all for today. Hope you liked the video. Don't forget to hit the like button because it helped me a lot. And also don't forget to subscribe to my channel so you can know when I upload the next videos. So see you next time in the next video. Bye!